for those who can't be here today. So as you know, one of the things I've been trying to do throughout this course is having everybody have an opportunity to talk a little bit about one of the assignments. There's still 4 people to go, but as of this moment, only one of them seems to be available. So Xingyao, you're available. Yay, you're online.
Yeah.
You got your camera. This is great. I don't have anybody else. So you know what? We'll make this pretty simple. I've got up on my screen. Let me just make sure I got the right person. I will share. Let me just make sure I've got the right. Yeah, that should work. Okay, so hopefully I haven't made this. Oh, what? Now it's not working. Why is it not working? Okay, how about that? Okay.
Yeah.
My computer's obviously having some issues today, but that's fine. Xingyao, this is your GitHub account, which is good.
Yeah.
Okay,
works,
so I've got it.
Yeah, it works. And I just upload twice because last time I found that it didn't show on my GitHub. It's not invalid. So I just recommitted.
Well, you got it figured out now. So that's perfect. So as I said, this is just to give everyone an opportunity to sort of share, because you're the only one who seems to be around today. I'll just check Slack one more time. No,
yes,
no one.
Thank you, Professor. I get this chance. Thank you.
Yeah, no. I said you got it done. So let's just talk about the first few questions of assignment 8, and we might need to push off the rest of assignment 8 till Thursday for the other people. But okay, so let's talk about this very first bit. So this is a question, an assignment all about pandas, and it says start by importing pandas, NumPy, and matplotlib. And then I see that you wrote this down.
Yeah.
So what does this do? This line.
It's just like you create the environment, or condition that, and it's just similar as last sentence assignment. The figure in the before one, show the right one, is that if you don't have this in the I just use the PyCharm, and if you don't use that figure, and it will show the right line on the PyCharm. So I just use the figure here.
Okay, no, I understand. So when we say importing, what we mean is these 2 lines.
Yeah, but actually, when I use my NumPy and it's stock here, so I just choose this one. And you said that use the NumPy as NP and pandas as PD, and I think that is more like the place when I write a fields. Before that, I will write this one to
Yeah. So what I'm saying is, typically in Python notebooks in Jupyter, we don't include these things as part of the notebook. The assumption is who's ever writing this notebook already has done this. So when we say importing pandas, NumPy, and matplotlib, all we mean are those lines.
Okay.
Yeah, but that's fine, no problem at all. So then you were asked to use the read CSV function. So the question was, could you use the lecture notes and load in the data? And what I saw you right here is you have a file name and this.
Last assignment, I use loading data, and it will load the CSV download to my laptop. Yeah. And for this assignment, I think what you mean is that I can download the whole file of strictly from the web. And also there a problem happened to my laptop is that my web is not Wi-Fi is not like continually, and in the question I remember is 15 or 16, there has a import US, and it got stuck because it's directly on this URL open the data file. So that's this point.
Okay, no, but you've done exactly what I was expecting. And the important bit is this isn't really a file, is it?
Yeah.
It's actually a URL. And that's one of the cool things about pandas is you can read not just files, which you can, but also data. So if the data was on the web and it was being updated every day, and it was always changing, this would always pull a fresh new copy of it down. And the other thing about read CSV is if you remember we did in assignment sort of 4, 5, and 6, we were doing all that Python stuff.
Yeah.
We read a lot of code to be able to load in a CSV file. Pandas handles all of that for us right away, which is awesome. And you've successfully displayed the first few rows of it because, like with Unix commands, head and tail, there's a head. So this is what the file looks like, right? So
yeah,
what we've got is these columns all the way through. That's fantastic.
Professor, that I have still have a question. When I do this part, you said that we show the first few lines, and I search on the line is the for the defined head and defined tail. It always show the 5 lines of the document. So if I want to show more like few lines, how do I change the description?
Well, so this head, this function here takes an argument. So if you said head like 20, you get the first 20 lines. Okay. But if you want to show some lines in the middle, what we would be doing is, and I'll just sort of look this up really quickly. If you look at the documentation for pandas, okay, there's this idea of eye lock, right? So what you can do with an eye lock, and I'll give you an example of it. So say you had things is you can choose with iLock any number of rows. So you'd say data frame dot iLock, and then you could put in a range, right? You could say I want rows 12 to 17. And so all df.head is doing is choosing the first few lines. So head and tail are just shortcuts to this iLock. And iLock just means integer location. So it's the certain rows in the data frame. Gotta get the right person. Okay, and then you showed the info, right?
Yeah.
And the point is, this is what the data types are. So just like in the Python stuff, if we were having to write our own CSV code, you'd have to handle the data types, right? Strings or floats or integers. Pandas is trying to do it by itself. You didn't pass in anything here, but it was able to figure out that the first thing is of type object. The second thing is a float, then a float, then a float, then a float, then what it's calling a mag type. They call that an object. So basically, anytime it's a number, it interpreted it as a number. And anytime it was not a number, it was being interpreted as a generic object, just a thing that it didn't understand any more than that. Okay, so now what we're going to do, and this is what I'll ask you in this code is, reread the data in such a way that all the date columns are identified as dates, and the earthquake ID is used as the index. Okay, so when we say reread the data, it means use read CSV again.
Yeah.
Right? So what you did is you took the data and you actually added in new columns, or you updated time and you updated.
Yeah.
To person the tanks, then turn them into times, and then you set the index. So this is the right answer. But you can actually do all of this straight from this line.
Yeah.
Yeah.
How can I just?
Sure. So if you look, and this is about looking into the documentation, there is an option called parse date. Sarah, what I'll do is I will go and look up pandas read CSV, and I'll show you how to do this. Pandas read CSV. Okay, so let's make this a bit bigger. Okay, so pandas read CSV does a lot of things. Okay, one of them that it knows how to do is, and I just need to use my alphabet here. Parse dates. So if you say parse dates equals true, anything that looks like a date will automatically be interpreted as a date, right? And the other thing you can do right in this command is you can say what the index column is. And if you look at the documentation for index column is the column to use as the row labels. So what you could do in your solution is you could just say PD read the CSV file name, comma, parse dates equals true, comma, use index equals ID. So it does exactly what you have done yourself, but that's all built into the command. And then of course you did add info to demonstrate you did it correctly, but there's actually ways of doing it a little bit simpler. But that's fantastic. We'll just finish off this sort of initial stuff. The question was, could you use the describe command? So I'll ask you this question about what we're getting. There are 1, 2, 3, 4, 5, 6, 7, 8 variables in this describe, but there were 13 variables. There are 13 columns or 14 columns. Why are there only 1, 2, 3, 4, 5, 6, 7, 8 columns in this describe, but 14 columns of data?
Because some of them are objects.
So when it does the describing, it's just taking numeric types, the floats and the integers, because it doesn't make any much sense to talk about the standard deviation of a bunch of places, right? Those aren't meaningful. So it's just giving you the initial descriptions about the count. And so this is a nice way of sort of looking at your data and just getting a sense of what it is. Like there are 120,000 rows. So you're never going to look through the whole table, but it tells you right away there's 120,000 rows. Of those, most of them have a magnitude, but not all, because that number is a bit smaller. And then these terms aren't always filled in. Some of them are empty. Here's the distribution, right? They're from the minimum to the maximum. Earthquakes occur all over the globe. They occur from relatively shallow to quite to deep, and they occur from magnitudes as small as like minus 1 to 8.2, and that information comes out of that describe. Okay, so let's ask you this question. So how could you use sort values to get the top 20 earthquakes by magnitude? So what does that command do? What did you type in?
Just like usual, I'll use the sort value function, and I use it. And when you want the top of 20, you just use the head 20 in the end, and when the title is the magnitude, and just when the defend information, it shows that this magnitude has a title is max. So I use the place is max and accidentally false. So this is the whole command here.
Yeah, so in this record, this is the largest earthquake in this record. So in 2014, that was the large earthquake that we had that particular year, and you have 20 of them. Okay, we'll ask you one more, and then we'll say we're done. What we want to do is extract the country using Panda's text data function. So I gave you a link, and I said go figure out from the documentation how to get the country from this table, right? Because if the original table doesn't have a country column, right? But it does have the place name in here.
Yeah.
Right? So let's see, how did you go about extracting the country from it? What is this line? What does this do?
That I define a new function.
You define a new function. Okay, so what does that function do?
It's country that I just like I just found that you have shown us the places, and here is actually the end of the places is the country.
Yeah.
Yeah, and I just like use the function the function in pandas place apply and to spell it into a new function, and that create a new
column, new column.
A column,
right?
Yeah, new column here.
Right. So we're splitting on the commas. So you're assuming there's only one comma in every line, and then you're basically just taking the second part of it all the way through.
So this should have a question if the country have two words in a name, maybe it get wrong.
Well, as long as there's only one comma, right? All the way through. And so your way works. I'm just trying to remember. Yeah. So so yours works, but sorry, I've lost my button here.
But not the perfect.
Okay. Oh, it'll reload. So yours works, but it didn't quite answer the question. In the sense of you had to write some code. So imagine you were new to Python as a language. This is a fairly complicated bit of logic, right? If you were a non-programmer, you may not immediately understand what apply, lambda, split, strip does. There is built into pandas some text data functions that handle this kind of thing for you. And so if you go to text data functions, okay, it's saying that I know how to actually work with text strings. So what you can do is you can just take the name of the column. So you would say df.place.str.split or .strip. Right, so here's an example where what they've done is taken the columns, think about the string name, and they've done a strip of it and use str dot. So what I would do, I think a cleaner way of doing it is to use something like this example, where you would do a df dot place dot str dot split dot string dot get, and then dot string dot, well, that's it. Basically, it's this line with this being replaced by a comma. So built into Python, pandas is a bunch of functionality to do what you had done with the lambdas, but it's actually in there as well. So my only suggestion to you is if you continue to use pandas in other projects,
I will more
read
focus
the
on that
documentation, because it does more than what you were able to do. But thanks very much, Danielle. I'm going to give you a check mark for that. There's still 3/4 of the, because there's still 3 people who haven't talked. So if you're not here today, but you're watching on the video, come on Thursday so I can give you an opportunity for a nice, easy check mark. Okay, anyways, thanks very much. I appreciate it. We'll go on to some content. Okay. So what I want to talk about today is I want to talk about something called Xarray and something called Dask. And for my life, my computer is fighting me today, and it is giving me some not clear error messages at all. So I might need to debug this, but you know what? I can always debug things in front of you. How hard could it be? That's supposed to be sarcastic, because debugging in front of people is always really problematic. So what we'll do is I will just open this up and we'll see how far we get. Okay, I need this link. Notebooks. No, not notebooks. Notebooks, Xarray. Okay, so we've been talking about fairly low-level things in Python, but as in data structures, right? So we've talked about arrays and lists, and we looked last lecture at different data structures, ways of actually saving that information to the disk. And what I had said was different science domains have different conventions they use for saving the data. And so in astronomy, we talked about the flexible image transport system, FITS. In oceanography, we talked about NetCDF, the network common data format. And all these formats are ways that people can exchange information back and forth. But when you actually go to use those tools, as something happens which is similar to what happens with CSV files. So, you know, with CSV files, if you were given the file, you can write your own code that would parse a CSV file. But like you discovered in assignments 5 and 6, you actually had to write a lot of code to be able to use it. Because those formats are so common, other people are able to have written packages which let you use those standardized formats in very efficient ways. So for CSV files, Pandas. Pandas is also great for Parquet and Avro and other types of records-based files. When you're talking about multidimensional files, NetCDF being the file format, and a few others which are gridded data, there's this package that's come online over the last 5 or 6 years called Xarray, which makes it really easy to deal with multi-dimensional gridded data. So it's a classic thing in science and physics that we will be able to talk about data that's described in multiple dimensions. So for example, let's take a property like the temperature on the surface of the Earth, right? So when you say how warm is the planet, the temperature of the Earth depends on some things. It depends upon where you are. It depends upon how far north or south you are, how far east or west, near the coast, in the middle of the continent. It also depends upon about time of year, right? It's warmer in the summer in the northern hemisphere than it is in the southern, than it is in the winter. So there's that dependence on time. So the way we write this mathematically is we say temperature, capital T, depends upon the position in latitude and longitude and what time of day it is. That describes the temperature of the Earth in mathematics. When we think about it in terms of an array, we might have a bunch of numbers that represent temperature or some other field like precipitation rate as a function of all these different latitudes, all these different longitudes at some function in time. And so the idea here is, how can we begin to load data in and process data that has this kind of description? Now, simpler methods like just flat out arrays. You can imagine having an array where you have the first column, the second column, and the third column. So you could imagine having your data, having one column being the latitude, one column being the longitude, and the third column being time. But it turns out, for readability, it gets very confusing very fast, the order in which you put these dimensions on. So what Xarray does is it gives you something called named dimensions that lets you ask questions that make more sense. Okay, so in an Xarray, just as an example of one of these more robust libraries, it has a concept similar to Pandas. Pandas has a data frame, which is this abstraction of a several series of records that are put together. A data array is a single higher dimensional, as in a square or a cube or some higher order dimensional data set. And several data arrays together are put into a data set. And the deal here is the data set, all the variables in the data set share the same coordinates and dimensions. A data array has the following properties. It's going to have some values. And so what an Xarray object is actually wrapping a lower level, purely numerical array. It's going to have metadata associated with the dimensions of the array are, data structure of a dictionary from Python that explains what the coordinates are, and another dictionary that have any attributes that you may have. So let me show you a particular example here. So I'm just going to bring in NumPy and Xarray as sort of low-level packages. Here is the simplest way of creating a Xarray data array. Okay, so it's pretty straightforward. Just like with NumPy, you just give it a list and you create it, and this is called a NumPy, a data array, as opposed to a NumPy array. And at this stage, you may go, well, what's the difference? What, if anything, is the difference between that and just having an array and saying array of 9, 0, 2, 1. Oh, right? Because there is a perfectly fine array. Here's just a different syntax. If this was all that it did, it'd be pretty boring, but it does more. what we can do is rather than just having to talk about the different dimensions, we can actually name them. So we can say this data 90210 is in the X dimension. So we can think about this not as some generic, the 0th dimension, but we can talk about it as being in the X dimension. So now this is the first value in X, the second value in X, the third value in X, and so on. So we've given a label to it. But things get interesting when we added coordinates. You can think about coordinates as ordinal variables or independent variables for a data set. So what we do is we say, okay, I've got my data. It's in the X direction, and here are the X coordinates. Now what this data array is doing is it's specifying that you've got this data, 9, 0, 2, 1, and 0, but here is the coordinates associated with it. So at X equals 10, we refer to position 9. At X equals 20, we think about position 0. At X equals 50, we think about the value 0. That's how these things are written up. And once you have it as a data array, like in pandas, you can just do plotting straight up. And so I can just say DA plot, whatever. DA is the thing that has both the data and its dimensions. And you just say make a plot of it. And what the tool is doing is saying, well, I know that this is the X array. This is the X dimension. So I'm going to give it that label of X. Where did it know the X from? It knows it because you called this dimension X. Now, one dimensional is pretty boring. It gets more interesting if you've got multi-dimensions. So in multiple dimensions, let's get some data. Let's grab one of my favorites, some Argo data. So I'm just going to download some Argo data. This is what you used in assignment number 7. And like in assignment number 7, inside this array is an array of salinities, which is salt content in the ocean, an array of temperatures, an array of levels, vertical positions in the ocean, an array of longitudes, dates, pressures, and latitudes. And what we saw in assignment 7 is I can build up each one of these things as an array. Okay, so I'm going to take each one of these pieces of data and load them in. And so now I have lon, dat, spt as different arrays. Now, instead of this, what I can do is I can wrap this stuff as a data array. And I can say, rather than thinking about salinity as just being this bunch of numbers, right? So it's just a bunch of numbers. The array itself is just so many rows and so many columns, right? 78 rows, 75 columns of data. Instead, let's give it some structure. Let's say, okay, this array has some names. It has this many levels. It has this many dates, because those what the rows and the columns correspond to. And furthermore, I'm actually going to tell the data structure that the coordinates of the levels are given by the array levels, and the coordinates of the dimension date are given by the date. And so when I do that, I get this much more rich data set, which has the data, but also the indices built right in there for the level column and the date column. And what that means is when I go to make a plot of this thing, I right away get levels labeled as levels, dates labeled as dates, a color bar, all sort of for me right away, because the package is making some heuristic assumptions about what this data is and how you'd like to display it. So very quickly, we can load the data in and then make a plot of it. Now, there's one other feature that these files have, and this is actually a property from data storage and data file formats, is not only do you want data and the coordinates and dimensions of the data, you also want to put in self-describing data that explains what is this data, where did it come from? And we call this metadata attributes. And so what you can do at either a data array or data set level is you can attach whatever type of attributes you want. In climate and weather forecasting, we have something called the CF conventions. And so some standard attributes that are out there are the units of something, and then maybe a long name, because S is not a very descriptive name. C, water salinity, is more specific. And so this is a typical way of thinking about the data. It has attributes, right? So this thing of numbers, what is it? Well, it's actually a seawater salinity, and it has units of PSUs. A PSU is a practical salinity unit. It's one of the ways of measuring salinity in the ocean. Several of these arrays together can be formed into what's called a data set. So in the same way that a pandas series is one column of a pandas data frame, one Xarray data array is one part of an Xarray data set. Okay, and you can put together data sets, but it's a little more syntactically complicated because you got more parts. So here is a data set for salinity, temperature, and pressure. Salinity has coordinates or dimensions of level and date. Temperature has dimensions of level and date. Pressure has dimensions of level and date. And here is the data in each one of them. The coordinates for levels and the coordinates of date are explicitly given. So if you think about this as a data set, we have all of the data associated with this Argo data set now in one tidy labeled package. We know the dimensions. It's a 75 dates, 78 levels. We no longer need to worry about, is that rows or columns for the two? And you've got all the data in one bundle. Well, the one thing we're missing is the latitude and the longitude. That was part of the original data set. We can add them. So I can just add in new variables. I can say, okay, the lon variable is the data lon, okay? And what it will do is says, okay, I don't know what dimension this is. I'll call it the lon dimension because I don't know. I've got no idea. Xarray doesn't know anything about physical units. It just says, okay, it's a new dimension, whatever. I'll just assume that it's in lon coordinates because I don't know. And then we could say, no, that's not quite right. The coordinate of lon is actually the same coordinate as date because what lon and lat and date are is where these Argo floats were at a specific point in time. So we delete that variable and we create a new thing. We say, okay, it's a date, but its date is its dimension, longitude is its value. Date is its dimension for latitude, latitude is its value. And we take a look at what's in there. Oh, I guess I should actually run that. And what you can see is now lon and lat are new data variables. They're not dimensions, they're just new variables that are indexed by date. When we have data variables are something that you can have arithmetic occur to. So if you have some data, whether it be salinity or temperature, or pressure, or longitude, latitude, one of the things you can do with Xarrays is you can do mathematical operations on them. So if I say an Argo times 10,000, okay, an Argo is a data set. It's several arrays. And what the timesing by 10,000 is going to do is take all of these data variables and multiply every one of them by 10,000. So salinity goes from 35 to 3.5 to 10 to the 5. Pressure goes from 6.8 to 6.8 times 10 to the 4. Latitude goes from 4719 to 4.7 times 10 to the 5, right? It's multiplied all of the data variables. But what it has not done is touch the coordinates. So when you do mathematics on these things, it's modifying the data variables, but not the coordinates. Now, I don't know why you'd want to multiply the data variables by 10,000, but you definitely don't want to modify the longitude and latitude. Longitudes and latitudes should stay as longitudes and latitudes. So what we can do is we can tell Argo, you know what, I want you to treat the variable lon and the variable lat, treat those as coordinates, right? So coordinates, as you can see, don't have to be the same as dimensions. You can have data with several different coordinates that share the same dimension. So this is useful for having data that might be represented by more than one coordinate system. You could have multiple different sets of coordinates all in the same dimension. So you could describe your data in different ways. Okay, so the symbols here, the reason they're bolded is because these are dimension coordinates. So these are coordinates which happen to also be dimensions. The ones that are in light font in this particular rendering of it are non-dimensional coordinates. You can make any variable a coordinate. Okay, why do we do this? Why do we set this all up? It allows for our analysis to be much more readable. If you recall that when we were doing just straight numpy arrays, if you wanted to pick it out a certain row or column, you had to index it, okay? So this line of code, in fact, I will go to cell and I'm going to go to clear this output. Okay, so here we go. If I just say, and I'll clear this output as well, so you can really see, well, not all output. Run current outputs, clear. Okay. If I just give you this line of code and I ask you, as a, doesn't matter if you're an oceanographer or not, what will you see when you make this plot? I don't think anybody could tell you. If you're plotting the second salinity, it doesn't make sense right away whether or not this is going to be a plot versus depth or a plot versus date. You're just saying the second, and you'd have to go back to the original file and think about rows versus columns. And so when you ran it, you might take a look at something. You're like, oh, I picked level 2, and I did all dates. And if you wanted to go back and pick a different level, right, you could do that. There's all level 1. There's all of level 10. And if you were looking at this and went, no, what I really want is I want to know how the salt content changes with depth, you can do it similar to you would with a numpy array. You can use a sliced notation. So you could say, okay, I want all the different rows, but the 10th column, and I could plot it. And this would be what the salinity is a function of level. This notation and this notation doesn't make sense to someone else, and it probably won't make sense to you after writing it and coming back to it. Alternatively, what we really want to say is, look, I want to plot the data where level equals 10, or I want to plot the data where the date is 2012, 10, 22. That's what I want to plot. And this is what Xarray is giving you. It's much more powerful to say, I want to plot salinity at level 2. And so it's just doing that. It's plotting the salinity at level 2. Okay, and if I want to do at level 10, that's the salinity at level 10. The code is telling us what we're going to get. Likewise for dates, okay? I want to plot the date as October 22nd, 22. Already, this compared to other ways of doing it is incredibly powerful. Remember that the data, the underlying data, is in rows and columns. So if you wanted to plot out the 22nd of October 2012, normally in other languages, you'd have to figure out what column, what column the 22nd of October 2012 corresponded to, and then pull out that column. You'd have to do some other arithmetic. With Xarray, it goes, well, these are just data types. I can convert this to a date time object. I can compare those things. I can find that particular day, okay? All the way through. In fact, what you can do, in the same way you can do with numpy arrays, you can actually do subset selections. You can support slicing. The syntax is a little awkward, but it's still pretty powerful. I could say, you know what I want? I want you to select all of the dates in the slice from October 1st to December 1st. And so what it's going to do is take the whole data set and just pick out the dates from the beginning of October to the beginning of December. So these dates are a nice way of looking at subparts of the data, okay? Not only can you do a selection on individual data variables, you can do a selection on the entire data set. So you can say, look, give me all the data from October the 22nd. And this is the data, right, from October the 22nd. There's only one date, and there are 78 levels all the way through. So this ability to select data makes the code clearer. That means someone who's following it can read it better, and it allows you to make less mistakes. Okay, where we use it is now that I've got this rich syntax, I can do mathematics on it. I don't know why you'd want to do it, but say you wanted to take the cosine of the temperature and times it by the square of the salinity. We can just do that in one go, right? I can take these fairly rich things and I can get a plot of it. So the key point here is this alpha itself is a data array. So when you do arithmetic or any kind of mathematics on Xarray objects, what comes out is another data array. And it's all point by point. So since temperature and salinity had levels and dates, well, that means this alpha thing is also going to have levels and dates. This has no physical meaning at all. This is just a pretty picture to demonstrate the feature of it. Broadcasting. If you remember about NumPy, broadcasting is the idea of taking two arrays that don't have the same shape and copying one of the columns or rows of that array in a way so the math still makes sense. The reality is broadcasting arrays in NumPy is a nightmare. It's hard to get right the first time. It's much easier if the data axes are labeled, right? So for example, if I wanted an array which was the levels times the latitudes, okay? The levels are all the vertical positions, the latitudes are all the north-south positions. What I could do is say levels times lat. Well, Argo, the dot lat, the latitudes are actually indexed by date, and so you're doing a bunch of levels by a bunch of dates. Because those are different dimensions, NumPy knows to broadcast those, so you get all possible combinations of levels and dates. And here are the latitudes for all possible combinations of levels and latitudes. Okay, more so when you're doing reductions on the data. So a reduction would be, an example, like a mean. If you have some data and you want to take the average over time, rather than saying the mean over column 2 or the mean over axis 1 or axis 0, what you can say is, look, I want you to take this data, and for every data variable, I want you to come up with the average over all time, right? So what this is going to do is take the data, and I'll remind you what the original data looks like. The original data is salinity, temperature, and pressure for multiple levels and multiple dates. So each one of these things is an array, and I can show you that array. Okay, this is the array. This is the array of salinities. It's a two-dimensional array. What I want to do is I want to say, okay, for salinity, temperature, and pressure, what's the average when you're taking the average over all time? So what you can do is you can say, take the average over all time, and what it's doing behind the scenes, it's saying, okay, what are my dimensions? I have a date dimension and a level dimension. Well, which one is the date dimension? It's the first one. Oh, you want me to take the average over the, well, I guess it's the second one, over the date dimension for all those three arrays. No problem. I'll do that for you. And then I get back this data. Date has disappeared because when you average over date, there's no more date dimension. But we very quickly come up with the average salinity, the average temperature, and the average pressure everywhere in the ocean. Okay, so if I plot salinity as an average, there's no more concept of dates. That's disappeared. This is just how it changes. Salinity is a function of how deep it is. There is something a bit weird about this data. Levels are not physical units. When I say I'm at level 32, I'm not really telling you how deep in the ocean I am. These idea of levels are just standardized levels that oceanographers use to indicate how deep you are. They take measurements at these standardized depths into the ocean, but they're not equally spaced. The levels are much more densely packed near the surface of the ocean than they are at depth. Instead, we use pressure to really represent how deep we are. So what we can do is we can take this data, okay, say the data for salinity as a function of level, and we can change it. And we can change it so that we can say, you know what, I'm going to add in a new dimension called pressure, okay, or mean pressure, average pressure. I'm going to swap the dimensions out. So before we talked about level, we're now going to talk about the average pressure. And so what this does is it changes the dimensions, okay? So we've gone from a data set which is indexed by level to an index of pressure coordinates. Now the dimension is the pressure coordinate. There still is a level, but now there's this new coordinate that's a named dimensional coordinate. So the data is now sorted in terms of date and mean pressure. Well, what does this have to do with anything? it means that when you plot it, if you think about 0 to 72 being the levels of the ocean, that's not really physical. It makes more sense to look at it like this, which pressure, and this is in decibars, so you can think of 1 decibar being 1 meter. So you could think of these units as being the first 2 kilometers of the ocean. It's the top few hundred meters which has all the variability in salinity. Most of the bottom part of the ocean is fairly uniform in terms of salinity all the way through. We can do the same thing not just with salinity, we could do it maybe with temperature. Okay? So in the ocean is, on the whole, most of it below a few hundred meters is generally all relatively the same temperature, 5.5, 4 degrees, somewhere in that ballpark. It's only warm or cold in the top part of the record. And so we've done a dimensional change all the way through. Once you have the ability to very quickly load in data and describe it, and do calculations like calculating the mean, you can do something which, at least in climate science, would have normally been a more complicated calculation, like figuring what's called climatology. Okay, so here's a different data set. So this is a data set which is based on satellites. So a satellite looks down at the surface of the Earth and can read off the temperature of the ocean at the surface. So we call this a sea surface temperature, or a CSST. So this data, which is saved in the netcdf format, when you read it and open it up with Xarray, actually gets populated as an Xarray object right away. So what's on the disk is netcdf, but one of the features of Xarray is it can read netcdf files in using an open data set, by analogy to OpenCSV and pandas, and you get right out this labeled dimensional coordinate data with all of its attributes, and says, well, what is this thing? Well, this is where it came from. This is its source. This is where we downloaded the file from originally. Okay, on the disk, okay, the data on the disk, this thing is a 42 megabyte file, and I'm describing it with all this rich metadata. Okay, so we don't have to type in ds.sst all the time. A common convention is just to relabel it. So SST now represents the data array. And I can do something very quick. I can say, you know what? This is data all over the world, at all latitudes and all longitudes, at many different times. Okay, and time 684. I'll show you the actual coordinates. What we're looking at here is basically the average temperature per month. Okay, this is 1960, January the 15th, 1960, February the 15th, Jan 1960, March the 15th. So basically the middle of the month, so it's the average temperature for that month from 1960 all the way up to 2016. So it's a 55-year time series of the temperature of the Earth. Well, what I can do is I can really quickly come up with the average temperature. I can say, you know what? I'm going to average that data over time, and I want to make a plot on a scale from -2 degrees Celsius to 30 degrees Celsius in one go, and I'm able to come up with this map of what the average long-term 50-year history is. What is the temperature of the ocean? And not surprisingly, it's warmer in the equator, and it's a lot colder around Newfoundland and Labrador. You see this cold bit right here? This is the North Atlantic Ocean. This is the Labrador Current coming in here. The water out around Newfoundland and Labrador is cold. Go swimming in the South Pacific. It's beautiful. You just sit there, you float, no problems at all. You don't go swimming in the middle of the North Atlantic. It's cold, as in it kills you kind of cold. You don't need to know how to swim if you're a fisherman in Newfoundland, because if you fall in the water, that's it. This is why you have to wear survival gear. It's a really dangerous place. It's very cold around Newfoundland in the middle of the ocean. But anyways, we're able to come up with this in a real quick instruction because we can talk about dimensionally labeled data. We can even do more so. We could say, you know what? I want you to come up with the average, in time, but also in longitude. So longitude is the east-west coordinate of the Earth. And if you do that in one command, what I can get is this plot. And it says, okay, as a function of the latitude, there's the equator right here. It is warmer near the equator and it drifts off. This shapes, the reason it's not perfectly smooth, right? Why it's not a perfect sort of line type shape is because you got these pesky things called continents that change the currents of the world. So if you got rid of the continents, this would be a very smooth, idealized shape, but we have continents, so that doesn't happen. Okay, so we could take this data and put it into a variable, say the zonal time mean. So zonal just means what we're doing is taking every, in the zonal direction, which is east-west, we're taking bands horizontally, all the data at a particular longitude, and we're averaging all that together. And so that's what a zonal mean is. And what you can do is you can take that data and then come up with some plots that start to have some interesting structure, right? The actual data, right? If I show you what SST mean looks like, well, let's say cell what 1960 12 no 01 15, is that going to it doesn't like that. Oh, I need to say what the coordinate is. Of course I do. Date equals. Date does not exist. What's it called? It's called time. It's called time. It's not called date. 1, 2, 3, 4, 5. There you go. So there's the actual data, and we'll give a plot of it so you can see what it looks like. So this is what the average zonal temperature looked like in January of 1960. And if I looked at this thing in, I don't know, June of 1960, the picture is going to change. We can look at all of those all the way through and subtract off the average temperature. So what we're doing is we're taking this average, this is sort of the mean, and we're taking the actual temperature at any one time and subtracting it off, and we can come up with this interesting plot. So without being climate scientists, can you see why you're getting the shape you're getting? So this is what we're looking at here is on the Earth, averaging the temperature of the sea in bands of constant latitude, looking at how the temperature changes with latitude from the north to the south, and we're looking at this thing in time. And you see these red and blue and red and blue and red and blue little signals. Just give yourself a moment, go, what am I looking at? What's it supposed to represent? And what I hope I can convince you of really quickly is this is just the seasonal cycle, right? All we're looking at here is blue, red, blue, red. Well, that's just winter, summer, winter, summer, winter, summer, winter, summer. The data is just showing that it's warmer in the summer and cooler in the winter. And the data down here, this is southern hemisphere winter, southern hemisphere summer. And they're alternating. So the data is actually split. So we're only looking at data in a little subset all the way through. In fact, we could take this data and do another selection, and we can say time equals slice. You know what? Let's go from 1990 to 1994. Yeah, method equals, actually that should work just by itself. So we'll do a little slice of that, right? And you can see that what we've done is I'm saying, you know, I want the data, but I only want to look at from 1990 to 1994. And so this is what the data looks like. There's a warm part, a cold, and a cold part. And this is just the seasonal cycle. And of course, the seasons in the northern and southern hemisphere are alternating. It's the ability to type in commands like this, which really have a lot of scientific merit, is why I'm advertising this package. And not just for climatology, but similar packages exist for all domains of science, something that really gives you some power to be able to ask scientific questions without having to do tons of coding. You just get to it right away. There's a few other here in terms of climatology, because you're not climate scientists. I don't know if you really care too much about it. So I will just show you one more thing just for some climate science. If you think about the sea surface temperature over the Earth, okay, and we subtract the average. Okay, so what we're doing here is we recognize there is a seasonal cycle. warm, cold, warm, cold, warm, cold, warm, cold. If we take that basic pattern and then take the average temperature for every January. So imagine taking every January from this data set. So this column right here, this column right here, this column right here, this column right here, grouping those together and then calculating the average January temperature. And we do the same thing for average February, average March, average April, May, June, and so on and so forth. What we can do is we can come up with what they call a climatology. Climatology is the average temperature or average salinity per month, because we know there's a seasonal cycle. So what we're doing here is we're grouping the data by time, by its month, coming up with the average of that. And you can see that what we're dealing with here is the average SST as a function of month being January, February, March, April, up to level 12. And so you're averaging this data on a month-by-month basis, and you're seeing at latitude 46, longitude 230, which is off the coast of California, it's colder in the winter, it's warmer in the summer, and so forth. If we were to take that data, I could plot it for a large part of the Earth, and I could see that there's this undulation where the warm part of the ocean alternates between the southern hemisphere and the northern hemisphere with the seasonal cycle. If I took this climatology and subtracted it off the temperature at any particular month, I would have what's called the anomaly. And the anomaly is the temperature of the ocean subtracting off what the average is or the normal is for that time of year. So this is what we call an anomaly. We don't really care about what the actual temperature is. We know that the temperature is getting warmer in the summer and colder in the winter. That's understood. The question that's of interest scientifically is any particular year, how much warmer or colder it is than the average. And so if you plot that data and then look at the standard deviation of it, you find out that even though all around the world, the temperatures are bouncing up and down all the time, where the water freezes in the Arctic and the Antarctic oceans, it's pretty boring. We don't get a lot of temperature variations. You do get a lot of temperature variations here in the Gulf Stream. This is as warm eddies carry fluid up on the East Coast, right? That's what keeps all of Europe sort of warm. There's some variability. This structure right here is a corresponding western boundary current in the Pacific Ocean called the Cretio. But this is an odd sort of thing. This structure, this thing that seems to be sticking out from the country of Peru into the Pacific Ocean. This is a feature, and it's being recognized right here by the variability or the large standard deviation, the temperature record, right on this spot. And so you may ask, and people do, what is this thing? Why is it occurring, and what does it mean? Well, we give this thing a name, and you might be familiar with it. It's called an El Nino, okay? Or an El Nino, La Nina, ENSO oscillation, Southern oscillation. It's a teleconnection between the atmosphere and the ocean that persists for several months, where warm water is pushed across the ocean, so this part warms up more than it normally does. And so one of the ways you can think about a El Nino, El Nina type of phenomena is to think about the average temperature inside this box. Basically, imagine a box, come up with its average temperature over a 3-month running mean. Okay, so every 3 months, take the temperature, as in take the January, February, March average temperature, then take the February, March, April average temperature, and then take the, whatever it would be, March, April, May average temperature. And then the question is, if when you look at that data, if the temperature is higher than normal for 5 months in a row, by at least 0.5 degrees, we call that an El Nino, or that's the oceanic Nino index. It's a way of declaring whether or not you're in an El Nino or La Nina phase, which has implications on the climate. So how would this be calculated using a package like Xarray? What you would do is you would say, okay, I got the anomaly. I want to select out this rectangle. Well, what's this rectangle? I want to go from -5 degrees south to +5 degrees north. So I'm just going to say latitude goes from -5 to +5. And the longitude is from 190 degrees west to 240 degrees, 190 degrees east to 240 degrees east, counting in a clockwise sense. So that defines the box. So this is the box over which we want to compute things. And then we could say, okay, what I need to do is come up with the average temperature in that region and compute a rolling difference all the way through. And so when you do that, you get a plot like this. So the orange line is this oceanic Nino index, and it's showing you whether or not the temperature in that box, in this part of the ocean, is higher than average, which means it's above 0, or lower than average. And anytime it crosses above 0.5, we say we're in an El Nino situation. And anytime we're below that, we're in a La Nina kind of situation. So in just a few lines of Python code, we've calculated this fairly impressive climatological index. So just for comparison, here is if you go onto the plot of the National Oceanographic and Atmospheric Agency's website, NOAA, here's their plot of the SST anomaly in that same region. And these two graphs have the same shape. Every time there's a pulse in one, there's a pulse in the other. It's the same data. But how would someone go about calculating this? And the power of these kind of packages is they're able to take instructions like this, okay? Take a box in the ocean, do a 5 consecutive 3-month running mean of the sea surface temperature, and find values that are greater than 0.5, okay? In one sentence, we can describe it, and in like 2 lines of code, we can calculate it. And so packages like this really help. And of course, once you've done a package like this, what you can do is you can label all the times where the data is in its Nino phase or its La Nina phase. And then you can go and make a plot of that data and say, okay, when you're in the Nino phase, here is the average anomaly. And you can see that for El Nino, it's a lot warmer in the Eastern Pacific than it normally is. And when you're in the La Nina phase, it's a lot colder than it normally is when you're in that phase, independent of month of the year, right? All the way through. And once you've done all this work, you can save this data to a netcdf file so that you can open this up and hand it to someone or submit it as further going. Okay, so Xarray as a package is not specific to climatology or oceanographic studies or atmosphere science. It's one of the places it came out of. But I think I've seen people who are doing things with Xarray and neuroscience. I thought I saw a talk somewhere here. Here we go. A completely different domain of science. Okay. So analyzing intracranial electrophysiology data with Xarray. Okay. So when you're dealing with neuroscience, these are like all the little sensors they put on the top of your head, right? You're generating data as time series. You care. This is what a typical plot looks like in an electroencephalograph, right? In EEC, ECG, and ECG, right? From neuroscience, right? These kind of data. Well, this data can be saved as a representative data format and then loaded in as an Xarray data set, okay? And then we can do selections of that data, right? So we may want to look at these records. What they care about in brain science is we want to know in this data record where something is happening at a certain criteria, as in we want to know what was going on when the scenario, right? In brain science, you look at your brain and then you have the patient do something and then you measure their brain. We want to look at this data set and figure out, give me all the brain data when the signal was not being, your brain wasn't doing whatever it was trying to work on. So you can use these Xarray things to very quickly do some analysis on it, okay? And so here what they're doing is they're doing some high pass filtering of it. So they're taking the data and getting rid of any of the low frequency undulations. And they're just keeping the high frequency noise. So again, a very small bit of code. This is basically saying Xarray, take the data, apply a filter, which is a mathematical operation, filter it out, and this becomes the record. So now you can start to see these little blips everywhere. And so you could group this data not by time, but you could group it by something else. You start to get these signals, and then do some analysis of it, right? And at this point, because I am not a brain scientist, I'm a climate and ocean scientist, I can recognize the code, I know what it's doing, but I don't know why this is a really important plot. I can tell you for El Nino and La Nina, but you can see how the pieces are all the same in the sense of this modality of working with data can make the code very, very descriptive. And in fact, this way of writing it up, you might recognize that this is actually just a Jupyter notebook. So what someone has done is they presented their science with both text, okay, an explanation of what's going on, and code right in there. The code, the text, and the figures all constitute one program. This is the programming. Compare this to a different model of computing where your code sat on a file far away from this interpretation. And you just have to depend upon the description of what this figure meant. Now what you can do is you can read what someone meant it to mean. Okay, this is a reduction. It reduces the number of dimensions. Well, okay, let's calculate the average across all epochs for each electrode time point. Now, maybe that makes sense to you, but if you're like, what did you really do? You can take a look at in the code. You can say, you actually took the mean over the epoch dimension. I get it. You're averaging over each epoch, which is a time period in the time signal, and then you're making a plot, right? The x coordinate is represented by time, and the channels, which I assume is just which indicator on your head, is indicated by the colors. So you can see from the code what the figure means. This is been discussed as one of the cleanest examples, this idea of notebooks and code and figures, of what Donald Knuth talked about as literal programming or literate programming as a way of describing what you're actually working on cleanly, so that someone else can read it. So I bring up Xarray as an example of a package which sits above and higher up than lower level storage, and either using these packages is advancing, is why Python is being used by scientists more and more. If you're not a practicing scientist in a domain, there is a lot of work to develop these packages. People are developing them for any particular domain of science. So Xarray and self-describing data, that was the first thing that I wanted to talk about today. I think we at this point we'll take like a 10-minute break, and then I'd like to give you a presentation on one other piece of technology called Dask, which is for doing distributed computing. In one of the lectures I uploaded via video, I talked about MPI. It's a very low-level way of doing distributed computations. I'd like to give you a flavor of a way of doing distributed big data computations in a fairly popular Python package. So we'll do that after a short break. So I'm thinking like back at, well, whatever it is, whatever 10 minutes from now is. 2:20. Let's say 2:20. We'll get back to it, and we'll talk about Dask. And then if you have any questions about the project, we can take those up. Anyways, we'll see you in just under 10 minutes. Cheers. Okay, well, welcome back. We'll continue on here. So what I'd like to do in this final little topic is to give you an example of some of the things you can do with parallel computing. You might recall, if you took the time to watch the pre-recorded lecture on high-performance computing and technology called MPI, message passing interface. There are technologies out there that let you leverage the use of multiple cores or multiple computers to solve your problem. And MPI is a fairly low-level way of doing that. So to actually take a code and modify it so that it's able to run efficiently on a high performance computing can actually be a significant amount of work. And so sometimes what we want is we want the ability to use parallel computing to do things in multiple cores or multiple computers at once, but we don't really want to be able, we don't really want to spend the time, like the many months required to rewrite the code. And so Dask is a library which has arisen over the last several years, which is providing that middle ground. Now, it comes out of a buzzword that's existed for a while, the idea of big data, right? You could think about companies involved in big data. A few years ago, you might have heard words like Hadoop or Spark being for big data. Big data is around machine learnings. This is a lot of where the money is for the development of this, in the sense that people want to analyze more and more things. Big data is data which is so big or so complex that the way we used to be able to do it doesn't work anymore. So what that means is if your computer is physically large enough that you can load in a million row data set into Excel, you're not running big data. What might have been big data back in the day when we only had like 4 megabytes of RAM, if your computer in front of you has, well, it probably has at least 2 gigabytes, if not 4 gigabytes, if not 8 gigabytes, then for you, really, any data set less than a gigabyte, that's not big data, because the ways you work with it are going to still work. They're going to fit into RAM. Whenever we're dealing with data sets which are bigger than the size of computer that you have access to, I'm going to classify that as a big data problem. So it's going to depend. Now, Earth Sciences, which is sort of my domain, have a lot of data sets which are big. Okay, so when we talk about data sets, we run climate forecasting simulations. Those data sets are 20 petabytes of data. Remote sensing, so satellite data, is growing by several tens of petabytes per year, per every couple of years, and it's going to keep on getting bigger. Astronomy is a big data set. Business and finance, if you think about, and marketing, you think about all the data and logs that a company like Amazon or Google generate in terms of the traffic. That's a lot of data. It's physically a ridiculous number of ones and zeros. It doesn't fit on a single hard drive. It doesn't even fit necessarily in a single rack of hard drives. You've got to spread these things over data centers to be able to fit. So what we're talking about here is problems in science that start to exceed really the amount of RAM you've got in your computer, okay? So your computer might have 2, 8, even 16 gigabytes of RAM. You can get, and it's totally reasonable to find machines that have 512 or 1024 gigabytes of RAM. They exist. They start to get a bit pricey, but they exist. But there are many data sets, 10 terabytes, 100 terabytes, 20 petabytes, which don't fit in anybody's computer. Okay, this is a problem that if it can fit in RAM, if it can't fit in RAM, but it can still fit on your hard drive, we can call that medium data, right? I can actually store it on a single hard drive. Big data is when we can't even put it into a single hard drive. We're going to spread it out, right? So these topics don't really come into play if it's a data file or your data fits on a USB key. Use traditional methods. But when you start to deal with large enough data sets, larger than a hard drive, definitely larger about the RAM of the computer, this is where this comes in. So Dask is a tool written coming out of the Python community that facilitates working with medium and big data. Okay, so data sets that are physically larger. In machine learning, you could imagine someone handing you a CSV file that is 20 gigabytes large. Okay, it might just be a bunch of log data, stock trading data, financial information, but 20 gigabyte CSV file. My understanding is if you try and load that into Excel, Excel will say no. I don't know if it will swear at you, but it will definitely say, I can't do it, sorry. Or here, I'll load the first 65,000 rows of your million row data set. You have to use some software to deal with data files of that size. So Dask is a platform that lets you do some of these things relatively near to the user in the sense that it's expressive, but still powerful enough to do some things. So Dask, it's sort of, Matt Rockland's one of the lead developers behind it. There's documentation, but I'm just going to demonstrate it as a way of getting into distributed and parallel programming. Okay, so Dask is built around the idea of a Dask array. Now, we talked about NumPy arrays. We talked about Xarray data arrays. These are called Dask arrays. A lot of carryover in the jargon, but the idea here is they're an array that Dask understands how to work with, and they're modeled after NumPy array. So a normal NumPy array. Okay, so here's a normal NumPy array, right? I want 1,000 rows, 4,000 columns of ones. Okay, so that's a data, and in my computer, that data is basically storing this much data all the way through. So we talked about what is the data type, right? It's a float 64. That means each one of these numbers is taking 64 bits or 8 bytes of data to store it. There are 1,000 times 4,000 of these things. There's 1,000 times 4,000 of these things. Okay, each one of those things is 8 bytes long. So there's 32,000 bytes represented by this array. Well, that calculation is done so often that there is a little attribute for n bytes that'll just calculate that for you. And we don't like to think necessarily in bytes. We want to think in kilobytes or in megabytes. So let's divide by 1,000,000, and that gets you to basically 32 meg. And I don't care if we're going to talk about gigabytes or gigabytes. It's not important for this discussion. A Dask array is an abstraction around the interface of a NumPy array. So if we do that, if we take a Dask array, it takes the same constructor as a NumPy array, that is the array ones, 1,000, 4,000. And nothing really interesting happens in this particular case. You still just get a big array. If you specify the chunk size, okay, the idea here is what we're going to do is we're going to think about the entire array, and we're going to break it up into components. And these components are called chunks. Each one of these chunks itself is a NumPy array that has a certain predefined size. Now, the sizes don't have to all be the same, but it's got some sort of block structure. So you can think of the overall array as having a shape of all the blue, and it's made up of these individual NumPy arrays, all the these parts. So if I have a array, which is not ones, I don't want the ones, I want shape. I want to show you what shape is. If I have something which is 1,000 by 4,000, and I specify a chunk shape of 1,000 by 1,000, what you can see is this array has been split up into chunks where each chunk is a 1,000 by 1,000 array. Each chunk is 8 megs of data. So what we've done is abstracted out the idea of an array from being a contiguous set of 32 megs of numbers into 4 contiguous arrays where each array is 8 megs apiece. Okay, so we're representing this array as 4 pieces. Now, we haven't actually done anything yet. Say, if you say what is a ones, it has this shape. Dask has only said, I'm describing the array. It is an array that will have 4,000 columns, 1,000 rows. It's broken up into these 4 pieces, but it actually hasn't computed anything yet. So no data is being stored in memory. When I say to a Dask object, .compute, that's when the computation actually occurs and I get the data that I want. Well, what's going on behind the scenes? Well, what's going behind the scenes can be visualized by what's called a Dask graph. And what a Dask graph is a way of how Dask is thinking about the data that you see. And so here we go. Here is the Dask graph. What we're doing is one, this array, this data array, or Dask array, can be thought of having 4 pieces. It's got the first piece, the second piece, the third piece, and the fourth piece. So to generate this function, what you need to do is for the first chunk, the 0, 0 chunk, this piece on the left, you're going to have to call the numpy function ones for a 1000 by 1000 array. For the second chunk, the chunk which is right here, Dask is going to call the numpy functions ones for a 1000 by 1000 array, and so on and so forth. Okay. What we often want to do is we want to generate this data and then do some more mathematics on it, some reduction on it. So say what you wanted to do is you wanted to have an array and you wanted to ask what the sum of all of these numbers are. Now, I understand that this is a trivial example because if you wanted to add up 1 plus 1 plus 1 plus 1, and there was 32,000 of them or 32 million of them, you could do some arithmetic. But let's imagine we had to do that problem for some scientific purpose. You could start with a Dask array and say dot sum, and then what it will do is parallelize that across all these different chunks. So here's what the Dask graph looks like for this guy. Okay, so as before, to generate the array of 4,000 columns, 1,000 rows of ones, what we're doing is we're splitting that into 4 pieces: 1,000 by 1,000 array, another 1,000 by 1,000 array, another 1,000 by 1,000 array, and another 1,000 by 1,000 array. If you want to add up all those ones together to come up with the sum of all the ones, what you can do is you can sum up each subarray independently. There's no need to add up all the numbers together. I can add up all the numbers in the first chunk, add up all the numbers in the second chunk, add up all the numbers in the third chunk, and the fourth chunk. And then take the sum of the numbers in the first chunk and the second chunk, add those together. Take the numbers in the second, third chunk, and the fourth chunk, add those together, and then add those together to give me this total sum, and that's my answer. And so this idea of a tree is how Dask is doing the calculation. Now, normally we could have a lot more chunks, and it will figure out how many levels of summing is needed to make this happen. Okay, let's make the calculation a little more complex. Okay, so because this one is sort of trivial. Here's another one. What I want to do is I want to take an array called ones. I want to flip it around. So take all the rows and invert them. So the first row becomes the last row, and the last row becomes the first row. Take the first column becomes the last column becomes it. Multiply it by itself, element by element, and then take the average of everything. Okay. So this is something you can imagine thinking about and working out what this would even mean. But Dask will give you the graph or the sequence of computations you need to get it done. Okay, so here's what it is. I'll walk you through it. Okay, you're thinking about the array as being 4 1,000 by 1,000 arrays separately. Okay, what you need to do if you need to do the transcription is you actually need to take this array and it gets multiplied by this array, but it also gets multiplied by this array. So basically you're relabeling or swapping the 0, 0 for the 0, 3 and the 0, 3 for the 0, 3 or 3, 0. You're doing the swap back and forth. And then you're taking the average of each chunks. And because the chunks are getting relabeled, when you actually think about taking the mean, and a mean of course is similar to a sum, it's really this chunk and this chunk that need to be averaged together, and this chunk and this chunk that need to be averaged together to get the final aggregate. So what Dask is doing is figuring out the order of operations to efficiently do this calculation. Now, if you are limited to 32 meg arrays, no one would bother with Dask. Dask is not needed for a problem as tiny as 1,000 by 1,000 arrays. So let's make it a little bit bigger, right? Here we're now dealing with an array which is 200,000 by 4,000. Okay, so in RAM, if you were to actually create this, you would need 6 gigabytes of RAM. And then if you were to invert it, you would need another 6 gigabytes of RAM. And then to multiply those together, you'd need another 6 gigabytes of RAM. So to do this calculation, I think you need about 18, 24 gigs of RAM on your computer. I don't think I have 16 or 18 gigs of RAM on this computer. I think this laptop's either an 8 or 16. It wouldn't fit, okay? This array, oh, 3.2, I made the problem bigger. Maybe we'll make it even bigger than possible. The graph is going to look a lot like this, okay? But if we were to actually plot it out, it would have thousands and thousands of circles. So don't try to visualize that. So let's do this. Let's do this calculation. Because the calculation can take a moment, what we can do is we can multiply this together and use something called a progress bar so that you can see the progress of these calculations. And each one of the little symbols you see. Well, I lost my progress bar. There used to be a progress bar. It clearly is not working, but there is. You can do progress bars. We'll ignore that for a moment. Here, we'll do this instead. We'll put a time. There. So this took 2.48 seconds to actually occur, right? If I make the problem a bit bigger, right, this is going to be the actual data will be 12.8 gigabytes. Okay, so it's doing some processing, it's doing some processing, it's doing some processing. We know multiplication is large, so it's able to do that calculation in five seconds. Okay, I would not be able to do this with NumPy array. So if I was to change the program and change this from here to here, I am hoping I'm going to run out. Okay, you know what? Because I don't want to crash my computer while I'm doing the video chat, I'm just going to say out loud that doing this will not work. If you try and allocate 12.8 gigs of RAM, I don't think I have that much free RAM available on this machine. Bad things will happen. I'll at least crash my kernel, if not bringing something else down. So it's the exact same as we did with NumPy arrays, but with Dask arrays, we're just creating this array in RAM. And it looks the way that it does. I'll just split it up. You see these lines? These are all supposed to represent, this is 40,000 rows, 4,000 columns, but each chunk is 1,000 by 1,000 little piece, right? So I'll make it even smaller. Here's a 4,000 by 4,000 grid broken up into 1,000 by 1,000 pieces. We were actually doing not 40,000 times 4,000, but 400,000, right? And you're getting a 12.8 gigabyte file, and you're doing some arithmetic on that, and able to do it relatively quickly. We don't just do simple things like adding and means. We can do any kind of multiplication. We could take this thing and break it up into the cosine squared, and then take the average, and this would be some sort of number. So this data set, this big ones, right, represents on disk a bunch of pieces. We're taking the square of something, the cosine of everything, squaring it, taking the average. When you're all done, that calculation, you're really just getting 4,000 numbers. For every column, you're getting one number. So it's a real reduction. The actual output isn't that big. If you want to make a visualization of this and plot it, well, what you can do is you can open up matplotlib, and when I actually want to plot it, plotting it will trigger a computation. So if I plot this, okay, it's going to go back and it's going to do this calculation, and when it's done, it's going to show it up for me. But I made the problem bigger, so maybe that was a bad thing to do. Because now I don't know if it's supposed to last like 2 seconds or 10 seconds. Be patient. Just be patient. Just be patient. Yeah, okay, there we go. It's unimpressive because it turns out the calculation, it's ones everywhere, you're going to get pretty boring data. But the point is we've just done a highly parallelized computation. Okay, let me demonstrate the parallelization that's going on here. When you are doing it this way, Dask is just spinning off threads, something in an operating system to allow parallel computation. You actually can have more control over what's going on. So here what I'm going to do is I'm going to spin up, and I hope this is not going to, I've already got it running. That's fine. I got 2 desks. It should be fine. I'm going to spin up a cluster of 4 workers. 4 workers is 4 separate programs that are concurrently running on my computer. And since my computer has, my computer has 26 gigs of RAM and it has 16 cores, what this basically is going to do is make it sure that every worker has 4 cores to work on. If I do this calculation, okay, I do this big calculation, what I can do is take a look at the status panel which is what this thing is over here. So you can actually see the work going on. Okay, so a lot of things jumping out on here. This big calc. What is big calc? Well, big calc is just this idea of taking the array times it by itself and taking the average. That's the calculation that we're doing. I'm doing this over 4 workers or 4 different copies of the program. You know what? Let's make it explicit. Let's do with 16 workers so that every worker is on its own core, right? So it's very clear with what we're dealing with. This is a little status panel that lets you see what's going on. So you can see that I've got different tasks. A task is one of those circles or squares you saw in the task graph. So if I start computing this, you'll see that on the left here, each one of these lines is a different CPU, and it has 100 tasks that it needs to do for itself. The colors indicate how much time each CPU is working on something. The tasks themselves are all very, very tiny, and there's many, many of them, which is why it goes pretty quickly. Let's do something a little bit more moderate here, okay, or a little bit more involved. So here is, I want random numbers. Let's give them away one. I'm going to have 4. Yeah, I think this will work not too bad. Let's go with, I don't know what, let's go with 8. Okay, so let's have 8 million numbers. So choose 8 million numbers and split that into 1 million numbers apiece. And then what I'm going to do is I'm going to calculate the histogram of that data. Okay, so the histogram is instantaneous because no data is actually being computed. Okay, it's only when you go to make the plot you actually get the data coming out, right? So if I go and I say, okay, what I'm going to do is do this and plot this data as you would a histogram. X is the actual, width. Where's the data? Hist is the actual data for the histogram. This is the picture it's going to produce. It's a histogram as it would be if normal distributed data. But I want to show you what's going on this side. So what you're seeing is it's generating the histogram in pieces. Okay, I'm not quite sure why we're not doing it continuously. That's throwing me off a little bit. Because I would see these things are all happening sequentially at the same time. Why? Oh, why is there not just 20 of them? It should be one go. There's no errors. There's something about this example that I'm not liking. Here, let me stop that. 20 workers. And we'll do this instead. This is a better way of looking at it. Okay, this is what we want this calculation to do. You're going to do a normal distribution over 8 different chunks. Each chunk is going to get a histogram, and then those histograms are all put together into one final histogram. I'm not quite sure why it's starting and stopping and starting and stopping and starting and stopping all the time. So my computer's acting weird today. But anyways, Dask is a lower level library that lets you do embarrassingly parallel things really, really easily. And actually things that are not quite so embarrassingly parallel, fairly straightforward. If you find yourself in a domain where you start to need problems that are either bigger than the amount of RAM you have on one computer, or you're given access to 4 or 8 or 12 or 64 computers, and you want to make them all work together to do something, because of your experience now with Python, I would encourage you to use something like Dask in your toolbox. Okay, so Dask is native Python. One of the things that it can do, I went to a Dask conference about 2 weeks ago. Not only does it do it for multiple computers, the newest version of this actually works for graphics card as well, right? You know, a graphics card can have like 512 CPUs. Dask can sit on top of that to leverage the power of your graphics card. It's used, pandas use it, Pandas users use it a lot. Machine learning people use it a lot. And it's supposed to be familiar if you're familiar with NumPy and Python, and it lets you do things at scale. Anyway, so it sort of sits on top of this ecosystem within the PyData community. So how does this get used in practice? Well, we can use it, say, on Xarray. So Xarray, here is some data. Okay, so this data is a bunch of netcdf files. They're satellite data, and you can see from the dates here, they're from different time periods. So this is a global temperature anomaly for April, the week, or for the season of April to September 2015. And then from, it's a rolling average, I guess is what it is. It's a bunch, no, I don't know. There's a lot of files there. There's a lot of files there. There are 365 files. So my guess is these are daily datas all the way through. Let's load it up and take a look at what we're dealing with here. Okay, so each one of these files, we talked about Xarray, each one of these files is a map of latitude and longitude of certain variables. Well, what's the variable? It's ADT, which is absolute dynamic topography. It's an oceanography thing. The water actually isn't flat, it moves up and down. And I don't mean by waves, it moves by underlying currents. Whatever. The data is showing you what this absolute dynamic topography is for each file, and each file is a different date, and there are 365 files. Okay, so let's think about this for a moment. This first file is 8 gigabytes of data. No, 8 megabytes of data. Okay, we have 365 of them. The actual data set is 25 years long. If you downloaded all of that, you'd have about 37 gigabytes of data on your hard drive. 37 gigabytes is more RAM than most people typically have on their laptops. How would I go processing this to come up with things like a climatology, an average per month, absolute dynamic topography of the Earth? So what it requires is taking all 25 years, picking out all the Januaries from all that data, and averaging all those together. And then loading the data up and loading up all the February data, averaging all that together to come up with the average February data. Xarray can open up a whole bunch of files at one time. So if we do something like this, what it's doing is it is going through each one of those files and opening it up, opening it up, opening it up, opening it up. Okay, so it's opening up 365 files. Each file is 720 by 1440. What Xarray is doing is letting me think about this array that's a time, latitude, and longitude array. It's letting me think about it as a 3-dimensional array, which in practice would be 3 gigabytes in size. But it's not actually loading all that data into memory. All that it's doing is saying, look, this is a 365 by 720 by 1440 dimensional array, but it's in pieces. And each piece is actually a slice that's 1 by 720 by 1440. This is the idea of chunking. So Xarray is sitting on top of Dask, which is sitting on top of these files. The values themselves are not displayed because that would require a computation. So if I do the same thing as I did before, which is just take the sea surface height, which is another word for the absolute dynamic topography out of this data, I can plot the data at one time. This will open one of those files so you can see what this thing actually looks like. So this is what I'm saying about the Earth. The ocean isn't actually flat. This is sea surface height. The scale here is in meters, and this is the whole ocean. We're not talking about really bumpy stuff. We're just saying that on left and right of the Gulf Stream, the water is about 2 or 3 meters higher on the right side than it is on the left side of the Gulf Stream. Whenever you have an eddy or a current, because of the pressure is lower in the center or higher in the center, you're going to get some raising or lowering of the water. So this is what one snapshot of this data looks like. What I can do is I can calculate the average over time by using a command like this. So what this is going to do, it's going to load that data in and calculate the average over time. You know what? I'm going to split this. I'm going to split it right here so you can really see what's going on with this data. Okay. So if I take the average over time, right, it will be an array of latitude by longitude because I've averaged over all time. But to actually compute this, I've got to do a lot of different things. Now, I'm not entirely sure. No, I don't want that. I want data. I have no idea if I'm going to be able to visualize this or not. 1500 is just the limit of what I want to do. But I want to see if I can get that array. Yeah, okay, you can sort of see it. So what it's doing is we've got 365 files. You see every one of those circles is a circle saying open data set. Each one of those is a file I got to open. For each one of those files, I'm averaging that file. And then because it's being efficient, it's going to take the average of those first 4 and put them together. Then the average of the next 4 and put them together. Put the average of the next 4 and put them together. And eventually, I'll be left with the average of the average of the average, which is a mean. Okay, so if I actually say go and do it, it takes a moment. But if I jump over here to this page, we should see the actual work going on. So each line represents the 16 CPUs on my computer. The blue squares is how much time they're doing. So they're opening a data set, and they're able to open 16 of this at a time, average them up, and then bring them all together. And you can see that the number of tasks is coming along through here. And once it's done loading all the files, I'll be at 100% tasks. I'm all over. So I've spread the workload of opening 365 files over 16 CPUs. I've parallelized my program without having to do anything. And that's the power of using these layered libraries. So this is what this data looks like. I'll give you a plot. Here we go. Here is the average over all time mean surface level. And then you could do other calculations with it. You can calculate anomalies. Okay. And when you calculate the anomaly, it's got to go back and open up all those files again. So you can see in the processing, what it's doing now is it's doing those 1,826 tasks, and it can do those fairly rapidly because they're parallelized, allowing us to make a plot. And this plot is the variance in sea surface height as a function of latitude. And then you could do some other calculations with it, like make a plot where you normalize this by the size, because how the data is scaled, each band of latitude is not the same size because, well, there's more data around the equator than there is at the poles all the way through. And so you get this curve that represents what the average sea height has done over the course of this year, right? And there's a seasonal cycle you're seeing popped out in here. Okay, the climatology is not important. That's a science-specific thing. What I wanted to get at is this idea of chunking, the idea of splitting up a very large array, which may only be understood abstractly or virtually into pieces, and doing computation on each piece separately. And libraries and schedulers like Dask are able to share that information with each other. So in the future, at some time, if you found yourself in need of doing a larger problem, several of you interested in machine learning, you may care to check out a tutorial or a documentation or watch a video on Dask. Pretty impressive bit of kit in terms of what is able to leverage without having to get into the weeds of a whole bunch of MPI level code. Anyway, so those are the packages and libraries that I wanted to share. This particular list is not extensive. As we talked about when we talked about the high energy particle physics stuff at CERN, the particular packages we end up using in science change every 5, 6, 7, 8 years, right? There are certain things which come and they go, but there are certain types of packages that you're always looking for. There will be a shell, a command line of some kind that if it's not bash, it will resemble bash. there will always be a role for a high-level scripting language like Python or R that has certain constructs, and it doesn't matter what it is. There are lots of visualization libraries out there, but they all will have to do the same concepts that Matplotlib requires. Data types. Different domains have different data types. It won't be NetCDF and Xarray, but it could be something else. So in the astronomy community, they use FITS. And if you look up AstroPy, you will find a ton of libraries that sit on top of that. Same thing in seismology, bioinformatics, different domains, whatever the specialty happens to be. We live in a world where we have access to high performance computing through Compute Canada. If you have need of that, I encourage you to reach out to AceNet, take some of their training on how to submit jobs to their cluster. But usually that requires writing some code in MPI, which is a bit of a barrier. If you find yourself just needing to have lots of CPUs that are all basically the same, technologies like Dask allow you to very rapidly distribute that information across links. So what this is supposed to do is giving you a snapshot into the types of tooling that we use when we're actually doing computing, right? We use more than just Excel. We use more than just straight up programming in a language like Java or C or simple Fortran. We work within a stack or a software stack of multiple layers. We definitely look at the documentation all the time to see what else is there, because most of the actual tasks have been done before. And we care about reproducibility and whether or not the code is readable for both someone else and yourself later on in your own research. So those are the topics that I have decided to include in this particular offering of the course. If you take it from a different person, they might have chosen different topics, but that's basically where we're at. Okay, on Thursday, because a few people still have not had a chance to present, and I like to give away free marks whenever I can, we'll take up the remaining parts of assignment 8. So if I've sent you a message on Slack and you're only hearing this now because you're watching the recording, I will give you an opportunity to get your check mark. We'll talk about the last little bit of assignment 8. I still got to sit down and actually mark assignment 7 and 8 so you know what your grades are, but I'm sure they will all be fine. So we'll take up the rest of assignment 8 on Thursday for a little bit. And then what I want to get into is the projects. Okay, so let me share a screen again and switch topics and talk about these projects. Okay, so nope, stop share. Share. This one. Wrong window. Okay, I will rework this document because this is the instructions I had from last year, but it'll be close to this, and I'll send you a link the day before. What we're going to do is we're going to do some sort of peer evaluation. Okay, so my responsibility as the instructor is to mark and evaluate all these things. So like 90% of the grade is going to come from me. But what I would like you to do as a group is look at each other's projects. So this is what I'm calling peer evaluation. Okay. It gives you a way of learning a little bit about some other software packages without going into the time. There are 19 people in this course. 19 presentations is going to be a little bit hard to fit and do any good discussion on in a group. We might just be able to fit it, but we'd be dealing with 5 and 10 minute presentations. It doesn't give people enough time to actually go into and look at the code you've written and how you've done your project together. And so what I'm going to do is I'm going to take the group and I'm going to split you into subgroups. Now, maybe I'll have 2 subgroups, 3 subgroups. I had more students when I taught it last year. So last year I went with 5 groups of 5. It may be 4 groups of 5. And what I'm going to do is I'm going to assign an order. Basically, everyone's going to get a group. And then within each group, what I'm going to do is say, okay, group 1 is going to look at project 1, then project 2, then project 3, project 4, then project 5 as an order. And the idea here, and I'll come up with a schedule so it's all given, and I'll try and have this out before the end of, Wednesday. On Wednesday, I'll publish this in advance of Thursday. I'll try and publish sort of the order in which I want things to go. The order will be random, but it makes it clear. And what I would like to do on Thursday is put you into small groups so you can evaluate each other's work. And I'll just pop into the different breakout rooms as we go. And what I want you to do is, for each person in that small group, that person will introduce whatever package or project that they've done and basically show their report, going, well, here's what I did. I was using this package. This is what it's for. Here is my computational steps that I chose, 1 and 2. Here's my visualization, and talk about it for 5, 6, 7 minutes. Then what I'm going to have each group do is actually go to GitHub for that student and look at their code, look at their Python code, look at their LaTeX code, look at their make files, and check, how readable is this? Did it make sense? Are you using the pieces in a way so that someone who's didn't do that project can sort of say, yeah, I see how this all would come together. I see how this would all work. Ideally, the project demonstrator may want to actually run their workflow by sharing their screen. That could be good, but I don't think there's enough time for everybody to install all the software needed to run all the documentation yourself. I will try and run your workflow on that shared server and handle any of the installation issues that are a problem. But I do want people to actually go into and take a look at that code and then come up with some questions about it. So about 8 minutes on, like 7, 8 minutes on a presentation, 7, 8 minutes, 9 minutes on reading each other's code, make files, Python scripts, how you're executing it, and then discuss in your small group that project. Basically, do a critique, an analysis on why did you do it this way? Did you think about doing it that way? Here's something I liked. Here's something I didn't like. And I really want you to have a discussion within your small group about that project and about that workflow. So just saying, yep, good, that doesn't count it. I want more than that. I want you to spend, each one of you spend a considerable amount of time on these projects. I want you to give each other 20, 25 minutes of your time on that project, right? In terms of you're looking at it, you're reviewing it, you're asking questions about it, and you're having a dialogue. There's no need to run ahead and skip to the next project. Spend the time on each project. Okay, once you've presented it, you've evaluated it, and you've discussed it, before we move on to the next project, and we'll always move on to the next project as a group, what I'll do is I'll have you finalize your peer evaluation form. Okay, what's a peer evaluation form? And again, I will be reworking this and send it out as a link on Wednesday. It'll be a little Google Forms project where you'll start by selecting whose project it is, and then you'll say, okay, the report. Does the report explain what the problem is? Does it identify the problem topic? Does it explain the thing? I think that is a 9 out of 10. I think this is a 2 out of 10. And you're ranking it relative to both your own project and the other projects in your group. Okay, so you're sort of coming up with a ranking from one to the other. That's the goal here. So about the report, about the visualizations, do they make sense? Is the code clear? About the computation that you're doing, visualization code, and the makefile. So basically 5, 0 to 10 questions. I might rework the actual questions and ask you about novelty or originality. But basically what I'm looking for is 5, 0 to 10 numbers on your group. And what I will do then is take those scores and put those into, average them, something I'll call a peer mark. And then I'll go through and give you a proper grading of all the different sub things, but it's a way of doing a peer evaluation. So if you want to call it presentations, if you want to call it evaluations, you're not supposed to come up with slides. You're not supposed to come up with a formal presentation. Your project is your presentation. The GitHub site, the PDF document, and the code itself. That's the topic of the presentation. Okay. For me to be able to set this up, I do need something from a few of you. So we talked about the project, and I don't know if everyone here who's attending right now has already done this or not, but no, I want this one here. This one. Okay, so I have no more pull requests. No one's giving me a pull request. Here we're at project topics. Okay, so I'm not presenting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Not bad. We're up to 14 out of 19. So there are 5 of you who I don't yet know even what your topic is. My hope,
Hello, Professor.
know what your topic is, and you just need to do a pull request to it to let the rest of us know. Yes, Arnav?
Sorry to interrupt. I actually submitted a pull request, I think. I submitted it twice. I don't know why isn't it working.
Pull requests?
Yeah, I actually was in the sign. There is a pan sign in the project list.
I don't see you in here. So did you submit a pull request?
Yeah,
No.
it's like editing the file. Can you go to the project list?
Well, yes.
The list of projects. Yeah,
Oh,
there is a pan mark at the right beside the monitor sign.
yes.
I clicked on that pan mark. No, not this one. I want the list of projects that student choose.
Which is where I was. List of projects. Yes. Go there. You edited it in, and then you submitted a pull request.
Yeah.
But you haven't submitted a pull request yet.
Let me do it again. Let me give it a try again.
Yeah. Really quickly, Arnab, what's your GitHub ID?
AR Barua. ARBARUA.
Okay. So there it is. There's your fork. Right. First thing, you're 2 commits behind. Let's go to projects. Right. So I don't even see you in there. Add Mohammed. Let's take a look at the history. Because this is you, right? I got the right person? Yeah, there you go. Hi, AutoLens, right?
Sorry?
Oh, I'm confused.
My name is Arnav Barua. That's not me.
Well, then you haven't made any commits. Well, that's just the full history. That's someone else who I've committed into it. So this is your copy of the project, right?
Yeah.
You made no commits to this.
Okay, so can you show me how to submit a pull request? I just edit the file.
Go to your package, right? Go to the list of projects, right?
Yeah.
I don't see your name in here. You're right. This will work. Click this button.
Yeah. Let me do this again.
Yeah. Go ahead. Okay. So you were just having a problem doing the pull request. It's not a big deal. It just gives you a practice of doing a pull request. Okay. So as Arnab's working on that, I'll just sort of finish it off. That's my vision for Thursday. So what that means is these projects need to be at least mostly done so that you can talk about them, right? So if I pick, I don't know, I don't even know who to pick. Michael, I'll pick you just because you're my mouse was floating on there. Okay, so this individual, right, has a README, right? You got some Python functions. You have a report.txt. You're not done yet, Mike, and that's totally fine. You just definitely want to have a report.pdf somewhere in here, right? And some figures.
Yeah, I'll add that this afternoon.
Yeah, you're working on it, but that's okay. But this is the presentation, right? This sort of these files and that final PDF, and then everyone else is going to dig into your .pies. But how do they know which one does what? That's because they're going to start by looking at this makefile, right? And it should be pretty self-explanatory. And yours looks pretty self-explanatory. Sure. But that's what we're looking for. So Mike, in principle, you could present right away. But someone else, and I don't know who to pick on. I don't know.
James, I had a question.
Yeah, doesn't matter. Yes. Go ahead.
Yeah, I was just wondering, did we actually need to use like the Conda create environment first? I sent you a message on the weekend. I'm not sure if you saw it or not yet, but for some reason, like the
work. No, you don't need to use that.
okay.
What I was looking for was whether or not your instructions were enough to get someone to install it on that machine. So whatever way you got it to run, that's what I need for it.
Okay, cool. Thanks.
Yeah, no problem at all. And if, to be clear, I'm going to try your instructions your way of doing it. And if it works, I give you a big check mark. And if I have to fix it and do it some other way, I'll give you a smaller check mark. And then go on to the next evaluation criteria.
Okay, thanks.
Okay. We're still just.
Professor, I submitted the request. Can you see it?
Oh, you submitted a request. You figured it out. So now I have a PR. Yay. Perfect. I love it. So merge it. Yep. You're done.
Thank you, Professor.
No problem at all.
I have a question regarding project.
Okay. So now I get to find out, what did you choose?
Yeah.
Oh, okay, sure. Oh, we're just starting. Of course, we're just getting going. Okay.
No, I'm actually working here.
Okay.
I haven't committed anything actually.
It's okay. You did the very first step. You got a repository, and you're going to do tie dynamics. Okay. What's your question about it?
I was just asking in the project instructions.
Yep.
So there is a line in, I think it's in step 5. Yeah, reproducible workflow. So there is a line, the second line, I think. If you need to download or create any input data, this should be done using a target with make. What does it mean actually? Can you re-explain it?
Okay, so if you need to download some file, like somewhere on the internet, there's a file you need. Okay, rather than the instructions being go to a web browser, type in this URL, choose save file, and then copy the thing. What I want you to do is, since we've learned about wget, actually make that a command inside the make file. So just to make it clear cut, these examples I was doing on right here, right? I needed this file to be able to do this workflow. So what that would mean as a, I'll just go to, I just want a nice, simple. I just want a terminal. I want a terminal to show you what I mean. New terminal. Yeah, I think you can read that. Okay, so if we have a make file, right? Okay, well, we'll do it this way. Let's say argo data.tar.gz. That's a file that we need to be able to run that, okay? Well, how do I get that file? Well, I needed to get it from some site. Oh boy, SIT on the internet.com/argodata.tz. Okay, and then what do I need to do with it? Well, I need to uncompress it because there should be a bunch of CSV files. Well, that's going to depend upon argodata.tar.gz. Well, what do I need to do? I need to extract out from argodata.tar.gz some file, because maybe that's inside that file. And then you might have to do some calculation, right? Compute result. Maybe you're saving it as a numpy file. That depends on argodata.csv. And here you might have a Python script my script.py, argo data.csv, compute results.np, right? And then you might have my plot.pdf, which depends upon computed results.np. How do you do this? Well, it's Python, my plotting code 1.np, and maybe it takes in an argument if you've written it this way. And there are other ways of doing makefiles which are more fancy, but basically there's something. There's going to be some code that basically looks like that. Okay, barring typos and recognizing that my file names are terrible, that's sort of what I mean. So this is you downloading data from the internet if you need it.
Okay, so the first line, that is the argo.tar.gz.
Yeah.
Will it actually download data, or it's just a common type statement?
No, so what this is saying is, so what does make do, right? It ensures that the thing on the left-hand side of the colon exists, right? So if I want to make report.pdf, what make will do is it'll first check, is there a report.txt on the file system? Yes, done. Is my plot.pdf on the file system? No. Oh, how do I make my plot.pdf? I need this file. Okay, well, how do I make that file? And it goes back up the tree until it gets to this one. It says, I need argodata.tar.gz to be on the disk. If it's not there, how do I create it? Well, how I create it is I download it from somewhere.
Okay, so this will not actually work like the Python code, right?
What do you mean it will not work like Python code? This is a makefile.
Yeah, so suppose in my Python code, I'm downloading some data using the URL you have given. You are writing in the makefile.
So you have a Python code that downloads data. Okay. So
Yeah.
so let me my data.csv. Okay. Well, my download data.py, right? That could be the dependency. And then you might run download data.py, my data.csv, or however you've written it, right? So you put a script that goes and uses some URL or whatever to download some data.
Okay, I got it. So I need separate script for the data
as well, right? But if it is just a URL, remember we have been learning about the command line. So you sure you couldn't just grab it in one go? It depends on the data.
It's actually I'm actually downloading data from Google Drive.
You're downloading data from Google Drive.
Yeah.
Okay. Google Drive is tricky.
I was actually able to download the data.
Well, you were able to download the data.
Yeah.
Remember about sharing and permissions. So
yeah, I actually
download the. So this is exactly what I'm getting at in terms of making sure things are reproducible. Google Drive is your own private Google Drive. How does someone else download from your Google Drive?
I actually create a shareable link. Okay. With that link, anyone can edit or view the files.
Okay.
And then I just edited the link so that the link can be used for downloading the data. And I think anyone with the link can download the data now.
Oh, okay. Okay. And this is a file you created.
Yeah, I actually created the file. I am actually using the file in my research. So I just took a little part of that and I'm using it for my project currently.
Okay, I understand. Now, I was assuming you were taking someone else's data, and I just didn't want you to take someone else's data and put it into your repo. I wanted to try and, this has to do with attribution, right? If you're using someone else's data, you want to sort of point people to that data. Oh, and you know what? Okay, does that answer your question?
Sorry.
Does that answer your question in terms of doing it? So something like this is fine?
Yeah. That's fine for me.
I just remembered that the 2 talks I just gave today, I wanted to give attribution and I forgot. So let me just, in terms of you're like, because someone's going to ask me, well, where's the notebooks for those lectures? Research in Earth Sciences. I think that's the one. Research computing, lectures. Here we go. I'm just going to drop those into the Slack channel for your wrap. Oh, and there you go. As I predicted in Slack, someone is asking exactly that question. Notes from today's class. Okay, so there was his Xarray one, and where did he put it? He had a whole more. These things, they all exist somewhere in here. I did get it from somewhere, so I can't imagine. There we go. Intermediate pandas. More. There's a link. Yeah, I'll just throw those into Slack for those who care about such things and ever need to look up. And somewhere through these links, you'll be able to find the original notebook, but there's an HTML version of it. Okay, I'm just going to put these into links. Xarray, put a link around that one, and then Dask around this one. Okay, were there any other questions that would be helpful to talk about as you're trying to get these projects off the ground?
So Professor, it's Arnav again.
Yes.
I'm just being sure. So can I use the data right now I'm using? Like this data is for my research, but I'm not using the whole data. I'm just using a portion, and it doesn't contain any personal information.
That should be just fine.
Okay, Professor, thank you.
Yeah,
I got it.
It's totally fine to use that that data. I assume is data that you want to take what an autocorrelation of.
Yeah. It's I'm actually using it for correlation. It's actually data related to human activity recognition using smartphone sensors.
Great. That's a totally realistic need for it. But hey, anyway.
I was just actually finding correlation between data from 2 subjects.
Yeah, it just the tie dynamics is a tiny little package, right? It doesn't do much more than different correlation methods. But it's an example of a computation.
Yeah, and I am trying to show some comparison. I think I will be able to present it on Thursday.
I'm looking forward to it. Okay, so just checking Slack. I don't see anyone else on Slack. Any other questions anyone has? Because I'm happy to let you go a little bit early so you can give you time to work on that project, because I know it's like every presentation I've ever given in my life. Most of the work happens in the day before. You might be better. Most of my work the day before. Yes. What's the question?
For reports, James, do you want those to be fairly general? Like I guess you just wanted a description of what we did for the task and how we did it, kind of in a general form, not so much describing.
It's very general. In some sense, it's a pretend science paper, right? Okay. Because the purpose is more how you would build a science paper as opposed to the actual science that you would do. Now, if you actually know some real science, if you're bringing in a domain you know something about, go ahead. But I'm not evaluating the science. I'm evaluating the computational science.
Okay, that's good. Thank you.
Okay, I think it's a good spot to stop. Again, if you haven't done a presentation in class, I do want to give you an opportunity to get that little, it's a tiny little check mark. It probably doesn't even matter in your old grade. But, you know, I know people care. So we'll take up a few people with assignment 8 right at the beginning of Thursday, and then I will have a schedule of how we're going to share this around. Again, if you have not submitted a pull request to me, I don't know what your topic is. I can't assign you to a group. I really do need this to have 19 names.
Professor, would you just have a look to my account, Omid, here in the list of projects?
Sure. What am I looking at?
Just open one of the tasks. Yeah. Task 1. I know.
Right.
I've tried to plot some of the results. In this project, we have some data sets. I mean that the data sets are delivered by the package, but
yeah, that's right. It runs different scenarios, right?
Yeah, in terms of computation, I didn't just get the gist, but I have just tried to do some filter and make it to some
I'll make it really
like
clear.
CSV and doing something.
In your case, the computation is the scenario.
Okay.
Right? RCP 45, that's the computation. When you do magic.run, that's the computation. Right?
Okay.
That takes a non-trivial amount of time to run. Right? So really what you're using this package to do is wrap this other piece of software called Magic C that runs something. Now, this thing, right, this data, that's your output. And the trick here is imagine, like, I don't know the software very well. I know there's a few built-in scenarios, but you can also do your own scenarios, right? Right. So you could, so the computation is exactly this.
Yeah, and I think it's, yeah, as you just mentioned, there is just some possibility to create our own scenarios using this package.
But for the purposes of what we're doing here, you could just have a single makefile target for each one of these. RCP26, RCP45, RCP60, RCP85. And there's something you want to get out of this scenario, right? There's some output, right? Well, here we go. You run the scenario, and then you save it as a file.
Yeah.
But the one thing I would not do is don't have a single script which collects all of your data for all of your scenarios. Okay, so rather than thinking about it as make data and having a loop that goes through here, 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 and here, and does the loop like you've done, let make control the flow of execution. So there's one Python script that runs one scenario that produces one CSV file.
Yeah, it's
okay. And then the idea is if there's another scenario,
it
needs a different, if it needs a different file output, it needs a different CSV file output.
Yes, so
I control the flow of execution.
Yeah, you mean that just working on one scenario and in turn not working on a bunch of them and all of them?
Well, so you may want to have all of them, but what I'm asking you to do is use make to drive the calculation. So the target won't be RCP dataset. The target might be RCP26 dataset.csv.
Yeah.
That's the target. What's the rule to make it? Well, the rule to make it is basically a little script that loads in the correct scenario and runs it.
Yeah.
Okay. And I want to express again, the point here is to demonstrate as a student in a course that you've learned how things work. So if you wrote a program that took a certain RCP argument as a command line argument, so it went Python space, whatever the script name is, RCP26, could you write some Python code that would execute that particular scenario and save it as RCP26 underscore dataset? Right? So you shouldn't have, if you want to run 3 different scenarios, you're not going to have 3 different Python scripts that each do the same thing with a change of one name. You'd have one script that takes an argument. Or maybe you have a function, right? But this is the output. This read RCP dataset CSV, but in fact, just this guy .csv, that is the output from the model. That's exactly what I want you to save to the disk.
Right.
Yeah, and you can think about whether or not CSV is the right file format for this data. Probably is. Right? And then you load that data back in, right? You could load it in from 3 files and reproduce a plot like this. Oh, I had one more thing to tell the group. Loading in 4 files and producing this plot, that's okay. It's not bad, especially when this plot, so this plot's a little more complicated because the year, the 760, 840, 880, that's not exactly the same as the units of time, right? So you have to do something a little bit special. But someone was asking me earlier today, we were having a conversation about time dynamics as a package, and someone was asking me, well, for the plot, could I just do a simple plot like, well, now I can't find the plot. I don't.
Professor, it's in the examples.
It was in the examples. Examples of using time dynamics. There we go. Well, no, I wanted to show something else. It wasn't time dynamics. It was something else. It was different projects. It doesn't matter who was talking to me. They were saying, well, would these plots be acceptable? And I said, well, yeah, but they're not great, right? If your plot is only a really simple, I called error bar and changed the limits. Yeah, that's technically fine, but it's really not stretching the envelope. You're not demonstrating any novelty, originality. It's not really at the scope of a graduate course. I know you can apply X versus Y data with dots. That's not special. So what I advised this particular student was, well, you know what? If you're gonna try this package, I guess this is the Eddie package. It's the same package, but like that would be a plot, which would be like, okay, there's some features there. That would be a plot. Okay, that's more interesting. You got subplots, you got graphs, you got histograms. That would be a plot that looks a bit interesting. You got color maps, you got this weird projection of the data. And there's one more, right? Something that has 2 plots. Now, the details of what plot it is can depend upon the package. But if you find yourself saying your 2 plots look like this guy, you may want to spend a bit more time going, can I do anything more interesting than just a straight up line plot? That would be the letter of the law, but not really the spirit of the law. Attempt to do something which is just a bit more interesting. Anyways, I thought I should bring that up as a comment. Okay. Stalling now. I don't need to keep you. Any other comments?
Excuse me, Professor.
Yes, Atia.
I just have question about step 5 in instruction. I I'm confused. I don't know what to do in Makefile.
Okay, well, let's help you out. So let's see, okay, so let's first review what step 5 is. So step 5, I said, a reproducible workflow, right? So this is what I was just writing out a moment ago. I'm gonna figure out where I put it. So this is an example of a workflow, okay? The goal that you're trying to make is you're trying to make this final report, right? Imagine you're publishing a scientific paper, report PDF, that's the end goal. What I want is a makefile that does everything that's needed to put that report back together, but done it in a way that it's broken up into pieces. So what does a report require? Well, a report requires a LaTeX file and every one of the files that go into that report, right? So you might have a first plot, a second plot, a third plot, and my plot is a terrible name, right? It really should be map global.pdf, I don't know, and then it should be summary, like maybe you have a plot that's called summary. I don't know what you've done, but you might have a few different things. And then the idea is like, so this would depend upon all of those things. And if you went through the make lesson, you would learn about variables, right? We talked about array variables. You could have, I'm going to get the notation right, but something the equivalent of and I'm not quite sure the syntax right now as I'm typing this out, but this idea that report depends upon that list of all of those plots. Well, how do I make a plot? A plot might depend upon some output file, some intermediate file that's the output of the computation, and then you've got a script that makes the plot. Where do I get this file from? Well, it depends upon some script that you've written that produces that. So a make file is something that if I went to the command line, I typed in make, it would do everything needs to be done to create a report.pdf. So let's take a look at your project in particular. So your project in particular, you have chosen to do Pi dynamics. Okay, great. So let me take a look at your example. So for your project, rename first example and second example to something a bit better, right? What do you mean by first example? What is it doing? Well, what is it doing? It is, you've got a plot. Okay, so if it's a plot, it's got to be plotting data. So what's the plot it is doing? It should be loading something from a disk. Okay, what you're doing is you are creating a brand new set of data and then plotting it. So you're missing the idea. The idea is this part of the code. This is your computation. Right, can you see how this is the computation step?
Yes.
Okay, so take this chunk of code, put this into a script that runs the simulation, right? Now, it could take arguments. Maybe 2000 is an argument, but this is a function that does something, right? As a given n, it produces, I guess, mean, is that your output? That's your output. Yeah, I think so. So take this array and then save that array to a disk. And then in another script, which is your plotting script, the very first step would be to load that array from the disk, and then it focuses only on making the plot.
Okay.
Okay, but this line right here is a bit weird, right? So see how you're calling Pi dynamics? Since that's part of the calculation, I would put this bit up here and save this output as well. So we're separating out the computation from the visualization.
Mm-hmm.
Okay, so
Okay.
does that make sense? So you're going to have a script that does something like this. You're going to have a script that does something like that. But use functions and arguments and stuff to spread it out. But it's all got the right parts. And then use a make file to control the order of execution of these different scripts.
Okay, thank you.
Okay, that sounds great.
So Professor, it's like generate the data by one script, perform it compression in another script, and data visualization in another script.
That's
Am I
right. We want those separate scripts, and the reason for doing that is because, like in this example, this particular calculation probably happens almost instantaneously. Okay, it happens very fast, and you'd never notice it. But in any real computational problem, this step can be minutes or hours or days or weeks, and you would never want to do this calculation again just because you want to change the color of the plot. The way it's written right now is to change the color of the plot means I have to rerun the entire calculation again and again and again for every change of the formatting.
Yes, Professor, I got it. Thank you so much.
On Slack, Brad has just asked, do you want us to delete all the DAT files after the computations are done and the plots are made so it's cleaner? I would have a line in your make file that cleans up your repository. So what would that look like? What you would do is you would have at the somewhere in your routine a make clean, and you probably want to remove any DAT files, remove any PYC files, remove any out files, whatever your routine makes as noise, so that you can really clean up your directory, right? So you can sort of start from scratch if you wanted to be clear. And you may even want to do something like this. Okay, so here's a common sort of rule, right? You might say make clean removes the DAT files, the out files, like all those pesky files you don't care about. But if you want to rerun your whole workflow, you may want to clean everything, but then actually blow away all the PDFs. So you might have another target called deep clean that does everything clean does and this. And right, and so the idea of make is it's sort of instead of the script, you can put those commands all the way in. You could have this be a shell script if it had a complexity. I don't know what kind of output files you're getting, but typically you can have several lines in a make file. And then your README would normally say type make to do this and type make clean to clean it up. You want to just document what this thing does as a file. The questions here are eating up all the time. It's like we're going to go the whole length. Just because there have been some questions. Anything else? Okay. Well, thanks very much, everybody. I will see you on Thursday, and we'll see what you've been working on in terms of these projects. Have a great middle part of the week, and we'll catch you later.